Good afternoon, everybody. Okay, uh, guys, hi to everybody. So, as I told you, you're going a bit fast, unfortunately, because we are running out of time. And I wish we could spend more time in chapter 6 on application, especially application parts. But we have only this week is left, and next week is Khmer New Year. Monday you have quiz. That's it. And also about quiz, we will see. Okay, most probably you will have quiz. If there is no quiz, then you will have final. Then you have to just prepare for final exam. Okay, and also preparing quiz means you have to in the same way. That means that you are preparing for your final exam. So once again, your final exam, I think it's on the 22nd or something. Okay, questions are all from chapter 5, 6, and 7. And chapter 7 is about, we are just actually adding some more functions that we have actually that we mentioned at the beginning of this course, right? That are transcendental functions. Okay, when I just say transcendental functions, we mean that it's not possible to obtain these functions using some mathematical symbols and like identity function, right? And these are like sine of x, cosine of x, by just adding some x or numbers or dividing by some stuff, right? We cannot obtain these functions. The only way to obtain is we must define these functions. So in this chapter, we're going to talk about these kind of functions and how to differentiate these functions and how to integrate these functions. And after that, again, the problems are similar, okay? So then we will start this chapter by inverse functions and their graphs, okay? And after we have some idea, actually you already studied this at high school, what we mean by inverse, and also I think you should know how to find the inverse of a function. And after that, we will define the natural logarithm. And after natural logarithm, based on this, we will actually define exponential functions. And after that, exponential changes, separable differential equations. And this part maybe I will skip because anyway, we are going to study this in differential equations and indeterminate forms and L'Hopital's rules, inverse trigonometric functions. That's it. Okay. So we are not going to cover hyperbolic functions and relative rates of growth because this hyperbolic functions, that is not much new. It's just the combination of exponential functions. That's why if you're interested, you can have a look and study this. And also relative rate of growth, that's also optional now. I will skip this. So today and tomorrow, maybe also Monday, I will make maybe one more or two more videos. We're going to cover from 7.1 to 7.6, okay? So today we will talk about 7.1 and 7.2. Tomorrow, 7.3, 7.5, 7.6. Now let's start with inverse functions and their graphs. Okay. So what we have here, first we will start with one-to-one functions, and after that we define inverse functions, and we'll talk about how to find inverses and derivatives of inverses of differential functions. Okay, and here there is nothing to memorize here. Again, I do not suggest to memorize these formulas. Maybe sometimes some functions you should know if it is easy. But actually, every time if you're solving a problem, if you are going through every step, that actually will be a good mental exercise for you. And of course, when you're solving maybe problems, right, maybe in the exam time or quiz time, at the time you are allowed to use a book or computer and everything. Right here you have everything, but the problem is, can you solve the problem using all these resources? Okay, that is what I'm expecting from you. So let's first talk about inverse functions. A function that undoes or inverse the effects of a function f is called the inverse of f. right? So for example, very simple example for this, when you are using a computer, for example, right, by mistake, sometimes you may delete a file, right? And after that, immediately you remember that that is an important file, you need it. So immediately, if you just press Control Z, right, it undoes the last operation. But now actually here, I can just use this as sequence, maybe, I don't know, maybe 3 or 4 at 5 or 6. Okay, if you just what is it? Press Control Z, it just undoes our last operations. Okay, it is exactly the same thing here. We're going to talk about the same thing here. For example, let's say if you're given this kind of function, for example, let's say f, okay, y is equal to, let's say this is f of x, that's equal to cube root of, what is it, 5x plus 2. Okay. Okay. 5x plus 2. All right. So now if I ask you to evaluate the value of this function at 2, right? So maybe not to use the same number, let me just write here 6 or even 7. Okay, 6, 7, okay, 7. Okay, let me just write here. It is minus 1. Okay. So now, if I ask what is the value of this function at 3? So when x equals 3, right here we have f of 3 is equal to cube root of, not 3, let's say this 4. And 7 times 4 minus 1, that's equal to cube root of 28. 28 minus 1 is 27. So cube root of 27, that's equal to 3. Okay. So now, if actually know that, we know that actually here the value of the function is 3. Okay. So the problem is, let's say I want to know, is this 3 or 4? 4, right? Okay. So this 4 is our input value, and this 3 is our output value, right? The result. Okay. So now if we have input value, we know how to obtain the output value, right? That is 3. So now if I ask the question, if you are given the output value, all right, how can I restore our function or get the input value, right? I should just do the same thing in reverse order, right? So simply, can you just tell me a function when I substitute here, for example, 3, it must give us this 4, okay? So that is a question. So now to do this one, now we need to find the inverse of this function, right? And usually how do we do that? So here, that means that y is equal to cube root of 7x minus 1. So that means that if x is given, if we need to find y, so now I need to express x in terms of y. So to do this one, for example, I just cube both sides. Here we have y cubed is equal to 7x minus 1. And from here, what is x? X is equal to y cubed plus 1 over 7. So now if you substitute, for example, what is it? 3 for y, right? So here we have 3 cubed plus 1 over 7, which is equal to 4. Okay. So that means that this function, and usually how do we denote this one? Actually, this function is called the inverse of this function because it is just undoing, right? Whatever this function does here. So we just usually denote this by f inverse of x. That's our x, which is equal to, here we have x cubed plus 1 over 7. Okay, we mean this. So our job is, if you're given any function, can you find its inverse, which actually undoes its operation? Before we continue, first we need to define this one-to-one functions, all right? Because that's important. When you just also get this, see here, it must give us only one value, not two. Otherwise, it cannot be a function, right? Because also it's inverse. Also, inverse must be a function. Function means we know that from the definition, when you just put any input, right, it must produce a single value, not two different values. So a function f of x is 1 to 1 on a domain D if f of x1 is not equal to f of x2 whenever x1 is not equal to x2. What does it mean? It means that if you are substituting two different values, right? So the function must produce two different values. So that actually we call that the function is 1 to 1. So simply, if you just draw, let's say this one is domain of the function, and this one is range, right? If you just pick any two different values, let's say this one is x1 and this one is x2, right? So the image of this x1 under this f, let's say it is y1. And also this image of this f x2, let's say it is y2 and under f, right? And we are saying that this image must be different if you're talking about two different input values. If it is so, then we say that this function is 1 to 1. Right? For example, every linear function, it is a 1 to 1. Every cubic function is a 1 to 1. But for example, let's say quadratic function, it's not a 1 to 1. I will talk about this test. Horizontal line test for 1 to 1 functions. A function y equals f of x is 1 to 1 if and only if its graph intersects each horizontal line at most once, right? Otherwise, it's not 1 to 1. You see here in this picture, right? If you look at this red line, if you draw a line anywhere, right? There's a horizontal line that is intersecting at only one point, which means that for every if you just actually substitute any two different values, it will produce two different values. And also the second one, y equals square root of x, right? Also, it's an example for 1 to 1 function. And how about this quadratic function, y is equal to x squared? As you see here, if you draw a horizontal line, right, this red line, it is intersecting the function at 2 points, right? So which means that two different points producing the same value. So I cannot go back. I cannot define any function. When I substitute here one, it produces one function. That actually contradicts the definition of a function. Because here, if you substitute 1 for y, right, it's producing -1 and 1. And that's why actually it must be 1 to 1 to be for the function to have inverse. And also another function, for example, sine of x, right? If you draw a line, it's intersecting here at two different points. So this is also not 1 to 1. But of course, here you may wonder, so Mr. Carson, if the function is not 1 to 1, can't we talk about its inverse? Of course we can, by actually bringing some restriction to its domain, right? And we can convert them into 1 to 1. For example, if you just consider this function over the interval from 0 to positive infinity, then this y is equal to x squared. It becomes 1 to 1. Why? Because its graph is something like this, right? Only this part. So that is 1 to 1. If you draw any horizontal line, there will be only one intersection point. And how about the second one? Also, y equals sine of x, right? If I just bring some restriction to its domain, for example, if I consider this from -pi/2 to pi/2, it becomes a 1 to 1. Okay, then actually we can talk about their inverses. Definition. So what is inverse function? Suppose that f is a 1 to 1 function on a domain D. Now we have idea what we mean by 1 to 1, right? With range R. The inverse function f inverse is defined by, what is it? F inverse of b is equal to a if f of a is equal to b. We are just interchanging the values of x and y, or we are just interchanging the roles of x and y. So here the domain of f inverse is R. The range of the original function, it is domain. And the range of f inverse is D. So if you look at this example, suppose a 1 to 1 function y equals f of x is given by a table of values. So when x equals 1, it is 3. When it is 2, it is 4.5, and blah, blah, blah. When it is 8, that is 34.5, right? And now if you talk about the inverses, right? So when I actually here, this our range values, right? The values in the range of f, it becomes domain. But when I substitute 3, it must produce 1. When it's 4.5, it is 2, right? So it will be here, this 3, 4.57, it becomes domain, and domain of the origin function, 1, 2, 3, 4. These are the range of the inverse of this function. Just interchanging. And finding the inverse. I mean, algebraically, how do you find this? And also geometrically, how do we draw the graph of the inverse function? Now, see here, to find the value of f at x, we start at x, go up to the curve, and then over to the y-axis, right? Usually, for example, here we have domain, this x-axis is the domain, right? We just move up vertically, that means parallel to the y-axis. When you just meet the graph, again, you just make a turn of 90 degrees, right? And just move until you meet the y-axis. Actually, that gives us what is the domain of f and the range of f, right? So if I just actually find this inverse at the time, this, what is it, red line, right? It becomes, what is it, the domain of the inverse of the function, because now I am actually substituting this output values as input values, right? So this blue line, actually, it gives us the range of the inverse of the function. And not geometrical, how they are related to each other. That means that they actually graphs, if you're talking about two functions, let's say f of x and its inverse, their graph is symmetric about the line y equals x. Okay, so just to draw the line, for example, the graph of the inverse of the function, first you need to draw the graph of the original function, and after the draw that y equals x, that's just a straight line passing through the origin, right? That makes an angle of 45 degrees with the x-axis, right? And after that, just a reflection of this point. How do we do that? Just put your ruler on the paper right here, the reflection of this one about the line, it is this. Another point, it is this. Another point, it is this, right? So after that, just join, after determining a few points and join them, you will get the graph of the inverse of the function. Okay, if we have more time, we can practice some questions later, or just practice question with your TAs. So find the inverse of y is equal to 2 over 3x plus 4, expressed as a function of x, right? We already did this kind of examples in chapter 1, if you remember, how to find the inverse of this function. As simply to find the inverse for a, I need to solve this equation for x, right? So here we have y is equal to 2 over 3x plus 4. So from here, 2 over 3x, that's equal to y minus 4. Multiply both sides by 3 and divide by 2. So x will be equal to 3y minus 12 over 2. So which is equal to 3 over 2y minus 6. So dot dot dot, the inverse of this function, the original function, is 3 over 2. Here we have x minus 6. Okay, so here you may want to, Mr. Cousin, why we are using x and x again? Okay, it doesn't matter. Here after the function, right? Usually, by convention, we use x, but of course you can write anything, maybe f inverse of t. And after all, it does not change the function of the function or the operation of the function. How about the second one? In a similar way, right, just we need to solve this for x. Since actually x is greater than or equal to 0, which means that, and also y will be greater than or equal to 0. So to solve this for x, so square root of both sides, so x will be equal to square root of y. Because here it is y is positive, while x is positive. That's why I'm just taking positive of this function. So dot dot dot, the inverse of the given function is square root of x. Guys, that's it about the one-to-one functions. And also here we have derivative, but I'll get back to this theorem again, because if I just tell you the theorem and try to, what is it, memorize again, I don't suggest it to memorize, right? You will see that actually differentiating an inverse function, also it is very easy. So in this theorem, it says that if f has an interval I as domain and f prime of x exists and is never 0 on I, then f inverse is differentiable at every point in its domain, the range of f. The value of f inverse prime at the point B in the domain of f inverse is the reciprocal of the value of f prime at the point A equals f inverse of B, blah, 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 blah. Okay, so here this is just a theorem. Okay, but here we're not going to use this theorem much. Okay, it's given here. That's why I'm going to talk with you about this. And the proof is quite simple. Let me just move to this side. Okay, what is the proof here? We know that here I have to show that if you differentiate, I mean the derivative of the inverse of the function at b is just equal to 1 over the derivative of the inverse, I mean the derivative of the function with respect to its inverse at b. Okay, so now we're just going to start with this to prove this theorem. I mean theorem just for, what is it? Again, mental exercise. Here we know that here f of f inverse of x, right? What is it? Is equal to x. Because first, if you take this inverse and find the value of f, right, that's equal to x. For example, here, let me just use here. I'm saying that this one f inverse is this, right? So what is f? F inverse of x equals f. What is f inverse of x? That's equal to square root of x. So here we have square root of x equals, what is our f function? F function is x squared. So here we have square root of x squared, right? So that's equal to x. The same thing here. That's what we're talking about here. Here we have f inverse of x. That's equal to f. What is f inverse of x? That is 3 over 2x minus 6, which is equal to, our function is 2 over 3x plus 4, right? It is 2 over 3 times x. Our input value here is 3 over 2x minus 6. And here we have plus 4. Now, if you simplify this, it'll see 2 over 3, 3 over 2. They cancel each other. It's x. And 2 over 3 times negative 6, that's equal to negative 4. Negative 4 plus 4, that's equal to 0. It's just equal to x. Because first, if you find its inverse, and after that, the evaluate the value of function at this point, it just gives us x. Anyway, using this one now, if you differentiate both sides with respect to x, right? And suppose that here we have some kind of function, right? Because here we have a composite function. So now if you differentiate both sides with respect to x, so here we have f, and I may just write like this, and here we have f inverse of x. Right? On the right hand side, I have d dx of x, right? So how do we differentiate the composite function? First, I need to differentiate f with respect to this, right, this input, which means that f inverse with respect to this one, right, times, and after that, I need to differentiate inside with respect to x, which means that here d dx, here we have f inverse of x. Here we have, what is it? Inverse. On the right hand side, if you differentiate x with respect to x, that's equal to 1. Right? So now from here, I'm looking for this one, right? If you look at the formula, I'm looking for this one, right? What is it? It is the derivative of the inverse of the function, right? The inverse of the function derivative. So that is, here we have f inverse x, because here we have okay, so we have d, right? So how I'm going to do this again? Let me just write here d dx, and if you just take this to the right hand side, here we have 1 over f prime, right? Here we have f inverse of x. Okay, so as see here, if this one is, as see here, our input value is b, so this one is b. Here we have b. This d dx f minus x, so this is just that thing. Okay. So anyway, that much is enough about this. What is it? One-to-one functions. Okay, guys, let's have a break. After 10 minutes, we will continue one more session, and after that, I will finish the class. Okay, like we will continue maybe after 9 minutes.